Now we pick up again at chapter 6, arrays. So we already did the basics of arrays, what arrays are, how they're indexed, that the first element is referred to as the 0th element. The addresses that we use to address each or access each element is called its index or subscript. And that the index does not necessarily have to be a number, but can be any expression that evaluates to a positive integer. So like other variables, arrays are also uninitialized, meaning that when you create them, unless you specify otherwise, they contain garbage values. Let's first look at how we can initialize an array. Now there's the simple way, of course, we can use a for loop and we can explicitly initialize each element of the array. And that is a perfectly valid solution. Sometimes this will be the only solution available to you depending on what specific values you want to initialize the elements to. So in this example over here, we are defining an array n of size 5 right in the main function. We have a for loop that I'm going to get into more detail about. And in each iteration of the for loop that starts from 0 and goes to less than 5, meaning from 0 to 4, that's 5 elements, right? It uses the counter variable I to access ni, the ith element of array n, and sets its value to 0. So this is the initialization step. This is followed by printing out a header, a 2-column header, element and value, just 2 strings, followed by the index number of each array element and the value that's stored in each element. There's one other new thing over here that you may have noticed, and that is the data type of the counter variable for both for loops. It's not an integer, it's not an unsigned integer, and by now you know that those can be used without any problem, or actually any other data type, many other data types can be used without any problem as a counter variable for a loop. But we're using something new over here, size underscore t. So before I talk about size underscore t, the rest is pretty straightforward, but before I talk about this new data type, let me show you the output for this program. So we have the header row, and that is followed by the index numbers 0, 1, 2, 3, 4 of all the 5 array elements, and the values with which we initialized all of those elements, 0 in this case. Now size underscore t is actually is a new variable type that was introduced sometime in the late 90s, early 2000s in C. So it is part of standard C, and it is basically the underlying data type is an unsigned integer. Now, this is slightly different from an unsigned integer in the sense that it can be large enough, or as large, you can store as large a number in it as you can possibly use to create the largest possible array for your system. So basically, in situations where an unsigned integer may or may not be able to store a large enough value to store a huge sized array, size underscore t can store that number. It is defined in another header file called std standarddefinition.h, standarddef.h, which is already included in standardio.h. That's why we did not include this header file in order to run that code. if on your system size throws an error, try including the standard def dot head.h file explicitly with a hash include. Only if you get an error. If you don't, okay? Only if needed. So we use the size underscore t variable to store whenever we use this data type whenever we want to store an array's size, or when we want to use it as a loop control or counter or index variable, like we just did in the for loop. So if you want to store an index value into an array. So in the size of, and in the example problems that we'll be doing, the codes that we'll be using, it will never make any difference whether you use unsigned int or size underscore t, but you should be aware of that this exists and why and what it's for. Now, in addition to using this method of using a for loop to initialize values of elements of an array, what you can also use is you can use something called an array initializer list, and the syntax for that is an equal sign and braces, curly braces specifically. So I'll show you slightly modified versions of this program, and in this one over here we have the same integer array of size 5, but in this one we're not initializing all the values to simply 0. Instead, we're initializing them to 32, 27, 64, 18, and 95. And after that, we're doing pretty much the same thing as before. We're printing out the column header, and then we have a for loop that has a size t counter variable I that goes from 0 to 4, less than 5, and prints out the indices and the values stored in each element of the array. And if you run this, the output will look something like this. So again, 0, 1, 2, 3, 4 are the indices of array elements, and 32, 27, 64, 18, and 95 the values stored in them. So as you can see, the first value is the value of n0, the second value goes into n1, third one goes into n2, fourth one goes into n3, and the last one goes into n4. Now, occasionally what may happen is that in this array initializer syntax, you may have fewer initial values than you have elements of the array. In that case, what will happen is the remaining elements of the array are automatically initialized to 0, which is very handy if what you want to do is initialize all elements of a very large array to 0. So for example, we have an array of size 10 and we want to initialize all elements to 0, so we could just write this. The first element, so n0, will be set to 0 because I said so over here, but because I have only included a single element over here, but I have 10 in the array, the other ones will all be set to 0 automatically. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So the remaining ones, n1 to n9, will become 0 automatically. The first one is being set to 0 explicitly. Now, if I had written, as an example, if instead of that I had written n10 equal to 1, then in that case n0 would have been equal to 1, and n1 to n9, so all the other values would still be equal to 0, just like before. But if you don't do that, arrays are not automatically initialized to 0, you have to do that one way or another, using a for loop or using the array initializer like this. So if you set at least first element to 0, the remaining ones will be automatically set to 0. A frequent mistake, a common programming error, forgetting to initialize elements of an array and just assuming they're set to something. Now, that was in case you have fewer initializing values over here than you have size in the array. What if the opposite happens? What if over here I have 6 elements, but the size of my array is only 5? That will return a syntax error. Now, if you want to reduce the possibility of a mistake, what you can also do is you can simply leave the size specified here in the definition of the array, you can leave that empty if you're initializing the values right there. So this, for example, will automatically create an array n of size 5 because I have 1, 2, 3, 4, 5 values over here. So this is another way to initialize while not making the mistake of having a mismatch between array size and initializing values. Now sometimes it's inconvenient, maybe your array is very large, maybe it's inconvenient to type out all the initial values of all elements of an array. Sometimes it's easier to do it by computing the value using a formula. So let me show you how that can work. And let me also show you another new thing. This over here is called a symbolic constant. This is also something new here. So for the moment, what we have done is this string. So we are using this new preprocessor directive hash define. What it does is it basically tells the compiler before really starting to compile this code, replace any time where you see this string, replace it with this string, which means in our case, the string size, which appears over here, and over here in 3 different places. This will be replaced by the digit 5, 5, and 5. I will talk about that in a little bit, why we would even want to do that. So, but for the moment, just in your mind, imagine size represents 5. So we are defining array S of size 5. We have a for loop over here. It has a counter variable j of type size underscore t, which we know by now. And we increment by 1 and we go from 0 to 4, less than 5. Okay. And we are initializing each element of S as 2 plus 2 times j. What that'll do is it will initialize S0 to S4 with the values 2, 4, 6, 8, and 10. And then we do what we did before. We print out a column header and we print out all the indices and array elements of S. When you run this, you get an output that looks like this, kind of familiar by now. Okay, so let me talk a little bit more about this preprocessor directive hash define. Now, what is the benefit of using it? Well, let's say right now we ran our code for an array S of size 5. Fine. But let's say now we want to rerun this program, but this time around we want to set the size of the array S to not 5, but 1000. I would have to change, if I wouldn't be using the hash defined preprocessor directive, I would have to change this 5 to 1000, this 5 to 1000, and this 5 to 1000. So the number 5 as a size of the array appears in 3 different places. If I'm making changes to my code, changing the size of the array, it could be very easy to forget one of those instances. In order to avoid such a problem, it is usually considered good programming practice to never use too many constants in the code, not any specific numbers. Instead, constants should be defined either as symbolic constants like this or as variables when possible. Unfortunately, we cannot have size be a proper variable because when you define an array, you will remember I told you you need to provide a number over here, and that's what we're doing. That's what hash define does. It's simply replacing every instance, every appearance of the string size with this character 5. Doesn't necessarily have to be a single character, could be an entire string, could be absolutely anything. Could be any text. The goal of doing so is to make programs more easily modifiable without having to make changes all through the CPP file. Don't forget never to end a hash define or hash include preprocessor directive with a semicolon. If you would do that over here, if you were to place a semicolon over here, what the compiler will do, it'll replace size with 5 semicolon, 5 semicolon, and 5 semicolon in all 3 places. And that's not what we want over here. So you'll frequently see symbolic constants like this being used, particularly when it comes to defining the size of arrays. Now, a symbolic constant is not, and I have to say that a symbolic constant is not a variable. You cannot assign a value to a symbolic constant. A symbolic constant is just a placeholder. It will be replaced in your code file with whatever you have specified in the hash defined preprocessor directive. In our example, size, anytime where we have size, it's going to be replaced by 5. It's also good practice to use only uppercase letters for symbolic constants so that we do not confuse, so the reader of your code, you yourself even, do not confuse a symbolic constant with a regular variable. If your symbolic constant is multiple words, you have to make sure that you have to connect those words with something. Usually what we do is we use underscore characters. So for example, if you have a symbolic constant called array size, you would use an underscore character over here. Let me quickly go through a couple of very simple examples. So here's one in which we have an array and we sum up the values contained in all elements of that 12 element integer array. And we're going to use the for statement's body to do that. So we're using a preprocessor directive hash define a symbolic constant size to symbolize the size of the array, and we're defining an array A of size 12, initializing it with these 12 numbers over here. We are also defining an integer total and initializing it to 0, and then we have a for loop which goes from 0 to 11. And in each iteration, we're adding the ith element of array A into total. And when we exit the for loop, we print out the total value. Run this code, and for this particular example, for these values, you'll see this total as 383. Here's another very simple application in which we collect survey results from, I think, 40 students or so. And the survey results are in the form of a number between 1 and 10. 1 means awful and 10 means excellent. So we basically have 40 numbers, and what we want to do is we want to count how many responses of value 1 do we have, how many of value 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's called a histogram. So basically what we want to do is we want to create a histogram from the 40 responses from the 40 students that we have. And what we're going to do for that is we're going to create an array of size 11 that we're going to call frequency. And each element is going to store the value of how many times a certain response has been given by students. Now, obviously, if the array is of size 11, there are only 10 possible responses. You may want to ask, why are we using an array of size 11? Why not an array of size 10? And the reason is it just makes for simpler code. We are not going to use the first element of the array, frequency 0. We're not going to use that. We're really going to start using the array element frequency 1 to frequency all the way to frequency 10. This is going to make indexing a little easier. So here's an example of that. So we have, in this one, we have two symbolic constants. One is called response size, which is the number of students that have answered, that have responded to the survey, and frequency size, the size of the array frequency, integer array. And we initialize it, all of its elements, to 0 using that handy shortcut that I just showed you before. And we have another second array called responses. So these are the answers we've gotten from students. We could even leave this over here empty if we wanted to, but we'll need to know the size of the array because we want to run the for loop for the same number of times. So might as well keep it. And after that, we have the different responses from students. So numbers between 1 and 10. 1, 2, 6, 4, 8, and so on. So first what we're going to do is we're going to go through this array responses in this particular for loop. We're going to start at 0, and we're going to go through all of the responses, all 40 responses. And what we're going to do is we're going to increment the element of the frequency array corresponding to, or that has the same index as, the answer given. So for example, the first time we go into the for loop over here, we increment frequency 1 with 1. The next time we'll add 1 to the value of frequency 2. And then we'll add 1 to frequency 6. We'll add 1 to frequency 4. We'll add 1 to frequency 8. That's what this loop over here is doing. When we're done, we want to print out the histogram, the survey results, and we're going to do that in this for loop over here. This is just the column header again, rating, and how many students have given that rating in the survey. So the output looks like this. We have the different rating levels, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And over here we have the number of times different students have given that rating. So 2 students said 1, 2 students said 2, 2 students said 3, 2 students said 4, 5 students said 5, 11 students said 6, 5 students said 7, 7 students said 8, 1 student gave a rating of 9, and 3 students gave a rating of 10. So as you can see, this is much easier, much more readable if we don't insist on using an array that is of the exact same size as the number of responses that we're going to store. Makes for more readable code. Okay, so that's just explanation of the previous example. Okay, one thing that you have to remember is that your C compiler does not know if you're trying to access an element of an array that does not exist. So for example, if the array n that you have created is of size 5, means you can go from n0 to n4. But once you have created array n, later on in the code, if you ask to access n10, your C compiler will not stop you. It will access whatever is at the 10th element location after the start of the array in your memory. Such a situation is called you basically walking off, or your program actually walking off beyond the end of the array. This is a problem because this way a program could be reading data values that do not belong to it, that belong to some other program. And this is, of course, a security problem. So as a programmer, you have to make sure, you have to keep track that you're not accidentally accessing an array element that doesn't exist, that is actually something else in your memory. So you have to keep track of the size of the array you're using. And this is actually something that happens surprisingly frequently in C. And we can build on the last version of the histogram example and make it slightly even more nicer by, instead of just adding printing out the table of values, the table of responses in the end, what we can actually do is print out a very simple graphical histogram. And let me show you the code for that. Quite straightforward. So let's say you already have computed a histogram, and this is it. You have 19, 3, 15, 7, and 11, and you print out a table header, print out the element or the array index, the value that's stored in there, so what we've done before, and after that you print out a graphical representation of that number. And we're going to do that by printing out as many asterisk characters as the value stored in that element of the array. So we have a for loop over here that prints out the number, the index, plus the value stored in the array. So in this case, I and ni. And after that, we have a for loop inside a for loop, a nested for loop. Because this is another loop, we need a different counter variable. So for the outer loop, we use counter variable I. For the inner one, we use counter variable j, an integer. And all we're doing is we're printing out the asterisk character for as many times as the value stored in ni, where ni is the ith element of array n. And when you print out the last character, exit the for loop, you print out, you break the, you go to the next line using by calling the puts function. And this is the output this will produce. So if you, maybe if you can, this is basically kind of like a horizontal bar chart of these values stored in these elements of the array n. You will also recall that when we studied random number generation, we did this example in which we simulated rolling a die for 60 million times. And back then, we had 6 faces of the die. And what we did was we had 6 variables to count which face of the die came up. Now, instead of creating 6 variables, I promised you back then that there's a slightly more elegant way of doing that, and that is, of course, using an array instead of 6 variables. The names of those variables back there were frequency 1, frequency 2, frequency 3, all the way to frequency 6. Instead, this time what we're going to do is we're going to use a symbolic constant size of value that will represent 7, because we want to skip the first element of the array. We want to skip 0. We're not going to use that. Similar to what we did for the survey example just now. And we create an unsigned integer array called frequency of size 7 and initialize all of its elements to 0. Seed the pseudo-random number generation function, and then run a for loop for 60 million times, in which we generate random numbers integers between 1 and 6, and store that in face, and then increment the value of frequency face. And at the end of that, we print out the values that we got, same as before, using a nice looking column header row followed by a for loop that prints out the value of the face plus the number of times it came up.